The interesting thing about what you're looking at is that none of the pixels were actually animated, but they're all just moving because of really simple logic that's applied to each pixel. Let me explain how it's done. But first, just take a look at it for a second. What's really awesome about it is that a lot of the behavior that the pixels have emerge out of simple rules. So none of it is actually programmed or animated. It's just it takes a life on its own. This is what cellular automata is, and this is a snake. That blue thing is a snake that eats the purple pixels. That's not really part of the demonstration, though. I mean, it's not part of the whole cellular automata. It's just there to make it continue. But anyway, this is how it works. So we have a single cell in the middle, and each cell has 8 neighbors. And depending on the status of its neighbors, when the game cycles through its frames, the next frame, the amount of neighbors it has will decide whether or not that cell lives or dies. So here's the rule for Conway's Game of Life, which is the most famous cellular automata, which is exactly what I just showed you. So if it has less than 2 or greater than 3 neighbors, then it would die, either by starvation or overpopulation. If it has only 2 neighbors, then it would survive. And if a dead pixel has 3 neighbors, then it would revive. It will come back to life, essentially. And these rules are really simple, but as you can see from the demonstration, the behavior that they show are incredibly complex. Now, how the rules are calculated is basically through a giant for loop. The for loop would go through every single pixel, basically every single cell in the grid, just like a two-dimensional matrix in this nested for loop. Count the neighbors, and based on how many neighbors, it would decide on the next color. And the color is what defines it as being alive or dead. Dead being black, and alive being not black, either green or some other color. Aside from that, we also have a snake that goes around and eats the purple pixels. And the reason for this is because if you leave the game alone for a long enough time, then nothing would happen. So I thought it was just interesting to add a snake that ruins the structure of the stable structure, so it would continue expanding. And now, as CPU versus GPU, the demo that I showed you is my CPU implementation, and this is just a graphic that I did to demonstrate the difference between the two programs that we wrote. The CPU would go through every single pixel or cell one by one in a single thread, just like the for loop would, whereas the GPU would index a whole block simultaneously and do the same calculation on each. See, this is why the Game of Life is such a perfect program to demonstrate GPU, because it's Cellular Automata is purely based on applying the same logic to a bunch of little things in a grid simultaneously. So it's really a perfect type of program to show what a GPU could do. Now, the problem, of course, happens when the problem with the CPU implementation happens when we have a much larger grid. Here, I'm gonna expand the grid size, so that will be maximum. You see. Okay, so once it's at its maximum size, it gets a lot slower, as you can see. It's not quite as snappy as it was when it was just when we were using a smaller resolution. It works, but the bigger it is, the bigger the grid, the more the CPU would struggle through loop through all those little cells at the same time. Oh, there's a floater there, a glider. See that thing? It moves by itself, no programming or nothing. It just emerges out of nothing, out of simple rules. And then let me deploy my snake, which there's a snake, little blue thing. You go around and eat stuff and get bigger. Yep. But anyway, so that's the problem with the CPU implementation is that we can't really make very um, large grids without the CPU struggling a bit. So my partner, whereas I'm going to do the CPU implementation, my partner is going to do the GPU implementation that we're going to show next, uh, and we're going to show that in the next part and compare the difference between the two. But before I do that, one more thing. Now, when I pause the game, you can see how many calculations it's done right here. Um, Cell calculations. Okay, so we were at 325 once we paused. So let me actually just run it again. Like at a smaller scale. Yeah, so once it's small, it's really fast, but when there it is, the slower it becomes. There's our steak. All right, so once I pause, I'm gonna count about a minute. First, I'm gonna pause, right, and then a minute, and I'm gonna see how many calculations or how many times it loops through the grid in 1 minute. So okay, here we go. 1 minute goes now. Well, actually, let's do 30 seconds. There you go. That's 30 seconds. So we can see here that you have, okay, so at 30 seconds, we went 100 times. 100 times through the grid, and the grid is not very big. The grid is, it's a resolution of, I don't know. Okay, so 9 by 16 is the aspect ratio. 7, 630, no, wait. Yeah, it's 9 by 16 and times that by 10 and 7. But anyway, so my friend is going to do the GPU implementation for comparison.